Hi, folks. Looks like it's 1 minute after the hour, so we're going to go ahead and get started. Before Matt kicks off today's presentation, Stephen and I wanted to take a minute to recognize and thank Matt for his leadership and efforts to coordinate this landslide hazard seminar series. Today is Matt's final day as the official planner, organizer, and host before he hands the virtual reins over to our colleagues, John Perkins and Shelby Arndt. So today is the last meeting that Matt will be leading. This seminar actually started as an internal USGS meeting to share science within the landslide hazards program. In 2020, Matt was responsible for opening the meeting up to external presenters and viewers, which includes all of you folks, researchers, academics, students, and applied scientists. Today marks the 125th talk organized by Matt. If you tune in regularly, you know what a great job he does. He keeps us on time, seamlessly manages any technical difficulties, and facilitates an engaging question and answer session at the end of every talk. What you don't see, unless maybe you have been a presenter, is all the hard work that he does behind the scenes. He keeps our schedule full of excellent and relevant speakers, keeps our calendars up to date with meeting invites, and coordinates with every speaker to ensure that things run smoothly week after week. Matt also makes sure that every seminar is recorded and made publicly available on the USGS website and YouTube channel, which I should mention as of today have more than 100,000 views. Matt probably does lots of other things that I'm forgetting to mention here. I know that at the beginning of every seminar, he recognizes myself and Stephen, but please know Matt is the true force behind all of this, and none of us would be here today without all of his hard work. So Matt, as usual, it's been a pleasure to work with you. Thank you for everything that you've done for the landslide community in facilitating this sharing of science. You've definitely left big shoes to fill, but we're confident that when we return next year, that John and Shelby will continue the great work that you've started. So let's all just take a second and give Matt a virtual kudos before we start with today's speaker. So thanks, Matt.
Wow, hey, thank you so much. It's absolutely been my pleasure to work with Jamie and Stephen on this meeting, and also the speakers in the audience. I have to say, you know, earlier on, it was a little unknown how long we'd be able to keep this going, and folks would sometimes ask me that, you know, essentially if we'd run out of material. But I think one thing I've learned through this process is just our community is a lot bigger than perhaps you might recognize working, you know, in front of your computer every day. So I really appreciated how this meeting has opened up the me and my eyes to, you know, the scope of the landslide community and those folks who are doing this amazing work all over the world and in the United States. So thank you so much. Oh, that's really awesome. I have my kind of normal intro here, and I'm gonna try not to sound too robotic doing it, because I will say thank you to Jamie and Stephen in it. So hi folks, for the last time, my name is Matt Thomas, and thank you for joining the USGS Landslide Hazard Seminar. This meeting is hosted by the Landslide Hazard Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We're going to take questions at the end of today's talk. So if you're not intending to speak, in the meantime, please just do the best you can to make sure your video camera is off and your microphone is muted. It's my pleasure today to introduce Maryn Sanders and David Souza. Maryn is a PhD candidate at the University of Oregon and an NSF graduate research fellow working with Josh Roaring. And David is a PhD candidate as well at Oregon State University, working with Ben Lashinsky. They both shared with me today that they're fourth-year PhDs, so they're really in that grind stage that we can all appreciate. And but we're going to see some of the fruits of their labor today, and I know folks are excited to hear about it. So, Maryn, I'm going to go ahead and kick it off to you. Thank you.
Awesome. Yeah, thank you, Matt, for the introductions. And I'm going to get us started with a kind of overarching motivation for David and I's work. And then about 10 minutes in, we'll be splitting off into our respective talks. And so the title for our seminar is Controls on Post-Fire Debris Flows in Oregon. And David and I just want to shout out our awesome post-fire debris flow working group, who without the support of, we would not be here, which includes, again, David's advisor, Ben Lashinsky at OSU, my advisor, Josh Roaring at U of O, as well as Mike Olson at OSU, and Francis Rangers and Nick Matthews at the USGS, Bill Burns at Dogami, Nancy Calhoun at the Washington Geologic Survey, and Mike Zimmerman at ODOT. And in Oregon in 2020, we saw some of the largest wildfires on record erupt across the Western Cascades of Oregon. These fires are still some of the largest on record. They're in the top 20 in size that have affected the state on historical record. We saw a lot of these wildfires are affecting really high landslide susceptibility zones in Oregon. So you can see the overlap with these medium to high regions. And so we can ask, how will these already landslide prone regions in Oregon respond to wildfire, especially as fires are becoming larger and more frequent? And a lot of what we know about post-wildfire debris flows comes from Southern California. So this is just an example of the USGS post-fire debris flow hazard assessment in Southern California for the Thomas Fire that occurred in 2017. We can see this projection between low, medium, and high debris flow hazard within catchments that were affected by the Thomas Fire. And we know following this fire, a little bit north of Montecito, outside of Santa Barbara, out of these really high debris flow hazard catchments, we saw multiple debris flows that were runoff initiated come down these catchments, inundate neighborhoods, and take the lives of multiple folks living in those neighborhoods. And they were incredibly catastrophic landslides that initiated before the fire was even contained. And I'll walk you through the recipe for such a rapid debris flow response. And some of these observations from California include this study from Roman DiBiase and Mike Lamb in 2013 that show vegetation in Southern California can literally get in the way and dam sediment that's traveling down hill slopes. And so when you burn all that sediment away, you're releasing all the sediment and allowing it to thus travel down the hill slopes towards channels. This is just an example of that playing out from an image from Marissa Pluchas's 2021 paper, where they also looked at post-fire ravel. This is before the storm, before the next storm hits. You can see all these lower order valleys are now loaded with ravel and channels are filled with sediment. And furthermore, when you burn this Southern California vegetation, there's also this oily substance all over the leaves and bark of this vegetation that leaves behind a hydrophobic layer over the surface. And so when that first rainfall comes, you have all the sediment loaded and none of the water can infiltrate into the soil. It's all running off over the surface, taking all the sediment that's left behind and kind of priming this landscape for immediate post-fire response. And so it's a little bit contradictory from the observations that we've made so far in Oregon. And so this is a study from Molly Jackson and Josh Roaring that was published in 2009, cataloging this geomorphic response in post-fire steep forested landscapes in the Oregon Coast Range. Similar to Southern California, they saw ravel on steep hill slopes, and they also saw a hydrophobic layer that was forming, but it was patchy and still allowed for infiltration to occur. And so you can see this dry soil layer is sandwiched in by these saturated layers. And so you can imagine that you might be seeing different initiation mechanisms rather than runoff, maybe more infiltration-driven shallow landslides. And that's further driven by this observation of progressive reduction in root strength in this landscape. So again, we're in a forested ecosystem. And if we measure those forest roots for a healthy landscape, as you increase in diameter, you increase in your root tensile strength. And after a fire, the magnitude of that relationship drops entirely from 1 month to 10 months to 4 years following the fire. So you see this progressive reduction over a long period of time where potentially you could be crossing some landslide initiation threshold over a much longer period of time because of this fire. And another observation that we have from Oregon comes from this publication by Sarah Wall, Josh Roaring, and Francis Ringers in 2020, where they went out and observed a runoff-initiated post-fire debris flow in the Western Cascades of Oregon. So more similar to Southern California. They saw this debris flow occur and saw pervasive reelings, a hydrophobic layer forming, but they did see a little bit of a delay in that debris flow event. It occurred about a year following the fire. And they went out, like I said, and measured a hydrophobic layer forming and found hydrologic conductivity values similar to what they measured in the Thomas Fire. So about, 25 millimeters per hour, whereas the Thomas Fire was also of that same order of magnitude, as well as other various burned regions in Southern California. And that matched the peak rainfall intensity that was falling nearby. And so when your rainfall rate is matching or overcoming that hydrologic conductivity, you start to drive runoff initiation processes, similar to what we see in Southern California. And so we're seeing observations that are similar, but also kind of diverging from what's happening in Southern California. And when we apply these emergency assessment models from the USGS to places like this 2017 Eagle Creek fire that occurred in Oregon, we know that this model is trained on Southern California, and we know that processes that are occurring are much different. Different initiation mechanisms that are driven by different climate, vegetation, and soil properties. And also we're seeing different timescales of debris flow response. So again, in Southern California, we saw debris flow events occurring before the fire was even contained. And if we look at this hypothetical precipitation threshold plot, where you have some pre-fire threshold, my Teams thing is keep getting in the way of my mouse. We have some pre-fire threshold that right after the fire drops for Southern California, and then whatever storm comes next can trigger debris flow. However, we also see a relatively rapid vegetation recovery, so that you might be returning to your pre-fire threshold within a few years following the fire. This is just an image from the headwaters of the Cold Spring Canyon, which is in one of those catchments that is north of Montecito, where you see a year's difference in vegetation growth about a year and a half following the fire. Promotes a relatively rapid recovery. Whereas in Oregon, we see debris flow events occurring years following the fire. So we see this progressive loss in strength and cohesion that might be allowing for progressively more and more lower precipitation events to initiate debris flows. We also see a much different recovery of the landscape. So this is pre-fire. We have this lush coniferous forest. In 6 years post-fire, we don't see the same scale anywhere near this pre-fire recovery. And so it's unclear what that Oregon post-fire recovery timeline looks like, whether it's on the order of decades or years as Southern California. And other information that we have coming out of Oregon are post-fire landslide inventories. And landslide inventories can be a really powerful way to understand these big picture patterns over large spatial scales. And so in 2017, that Eagle Creek fire erupted, and we had the opportunity to go out and map post-fire landslide events using differential LiDAR. And we mapped over 250 events following the fire and saw a peak in landslide occurrence about 3.5 years following the fire. And also in 2020, for those Labor Day fires, there's just a USGS data release that was authored by Brittany Slanders and others, where they mapped over 150 events using combined field and imaging methods across those 2020 Labor Day fires that I had mentioned at the beginning of my talk. And they observed landslides anywhere from 5 months to 2 years following the fire, but that inventory is capped for observations from 2020 to 2022. So I'm sure there are observations still to come in these burnt areas. And so we can return to that question, how will landslide-prone regions in Oregon respond to wildfire? And these are the two locations that I had mentioned where we have observations from, the Coast Range from that Jackson and Roaring paper from 2009 and Black Crater from the wallpaper in 2020. And we know that we have different initiation mechanisms within these two studies. And so that variability in post-fire response is probably driven by local to regional scale soil properties, sediment production rates, and ecological regimes. And these new inventories that we're starting to create can provide opportunities to dig deeper into how variable that post-fire response is in different places across the state. And so I'll take a breath here and just introduce the titles of our two talks, and then we'll split off into mine. Post-fire debris flow hazard in steep transient catchments of the Columbia River Gorge, Oregon. And then David will finish us off with post-fire route dynamics and landslide risks in Western Oregon. And again, the title of my talk is Post-Fire Debris Hazard and Steep Transient Catchments of the Columbia River Gorge, Oregon. And I would not be doing my field site justice without showing an incredible photo of the gorge and just showing how drastic of a landscape it is. And so the Columbia River, we're looking eastward down upstream the river. And the Columbia River is cutting through an actively uplifting continental volcanic arc, the Cascadia Arc. And you can see these impressive basalt cliffs surrounding the Columbia River. And this river attracts tourists all over to all of its beautiful waterfalls. But geomorphically speaking, like I said, the gorge is incredibly steep and rocky, and there's evidence of hazard everywhere that comes in the form of debris flows, rockfall, and shallow landsliding. It receives upwards of 250 centimeters of rainfall per year, as well as snow. And that rainfall amount supports the temperate to montane rainforest that you see scattering the cliffs in this image. Additionally, the basalt, or the bedrock, is primarily basalt. However, that varies in mechanical properties. See this more coherent colonnade overlying this columnar unit, which promotes this oversteepening and overhanging cliffs of these landscapes. We also have gentle over steep topography. So you have the Columbia River cutting into this volcanic arc, and this escarpment is retreating into this relict surface that is resurfaced by volcanic basalt flows coming from edifices scattering the gorge, as well as glacial imprinting. Additionally, we're in an actively uplifting volcanic arc that is uplifting at 0.2 millimeters per year. And so all in all, this is an incredibly rapidly evolving place. And in 2017, we throw the Eagle Creek fire into the mix. And again, this fire occurred about 30 miles east of Portland, a little bit north of one of those Cascade volcanoes, Mount Hood. And it was an incredibly disastrous fire. It was really hard to fight because of how steep the gorge is, and it burned almost 50,000 acres of the Oregon side of the Columbia River. And that post-fire working group that I mentioned earlier was smart enough to realize that we need to capture the baseline morphology of this landscape so we can understand just how much geomorphic change is going to happen following the fire. And so in 2018, they went out and collected LiDAR. And in 2009, we also had a LiDAR data set. And so using these two data sets, we could constrain a pre-fire landsliding rate in this region. And then in January 2021, we saw our first post-fire debris flows initiating from the Columbia River Gorge. And then we collected more LiDAR in January 2021, or following January 2021. Then we had additional events occur just a year later in January 2022, and we collected more LiDAR. And all of this information provided some really awesome opportunities to do some change detection, actually quantify how much work these debris flows were doing. And this is just an example of what that inventory looks like. And so you can see here, these red polygons are initiation sites for debris flows. These white polygons are transport pathways. And then this blue polygon is the ultimate deposition of that debris flow. And I urge you to go back to Bill Burns's USGS landslide seminar to check out all the details of how that inventory was made and some of the awesome outcomes that we've been starting to notice in that inventory. And if I take that inventory and map it out over this beautiful Google Earth imagery of the landscape, so right now we're looking south, here's Mount Hood, the Columbia River is flowing this way towards Portland on the right, and all those post-fire debris flows are in red, and those pre-fire debris flows from that 2009 to 2018 period are in green. And over that 9-year period, we mapped 50 pre-fire landslides. And from 2018 and 2022, we mapped over 250 landslides. So we saw a really a large increase in debris flow frequency. And also, if we look at the distribution of how these landslides are spaced in the gorge, we see a really high density of landslides in these 10 small catchments. And I call these catchments the Dodson catchments because they're pretty close to the, or actually the town of Dodson is at the base of them. And we can see that based on the morphology of the fans as well as these active debris flows, these fans are built primarily by debris flows through time. And we know that large fans mean a high sediment flux, and these are built by debris flows. That high sediment flux has to be coming from a high debris flow frequency, which means for us a really high hazard. And we saw that play out in January 2021 down this Levens Creek catchment where debris flow ran out and inundated this frontage road. And that followed a really intense rain on snow event that initiated most of the post-fire debris flows and actually took the life of a woman that was driving home from work on that frontage road. And you can see some of these ODOT vehicles for scale just for how big this depositional event was. However, this was not the first time that Levens Creek posed a threat to the communities at the outlets of these fans. In 1996, there was a long-duration 4-day rainfall event that initiated numerous debris flows across these Dodson catchments. They buried cars, derailed trains, and the event that came down the Levens Creek catchment actually destroyed this Royce family home that you can see in the foreground, but luckily no one was hurt. Then in 2001, there was another rain on snow event that initiated a debris flow event just west of Levens in the Rock of Ages Creek catchment that inundated the frontage road in a similar way that the 2021 event did. But again, luckily no one was hurt. So we have all of our information from 2009 to 2022 of our pre and post-fire conditions. However, we can extend these pre-fire observations back a little bit further to that 1996 and 2001 event. And furthermore, we also have some engineering reports that tell us events have been occurring here pretty frequently between 1962 and 1981, as well as word-of-mouth observations from 1918 of a large catastrophic event. So historically, if landslides are occurring all the time in the Dodson catchments, to what degree does fire alter this baseline capacity for landsliding? And I can argue that the debris flow fans indicate that this process has been taking place over thousands of years. So can we use this fan record to quantify this erosional capacity of fire to the overall hazard of this region? And previous studies have shown infrequent and large landsliding events typically dominate the long-term erosion rates. This study by Jim Kirsch and others in 2001 went out and measured cosmogenic nuclides, which gives you a long-term erosion rate, so over tens of thousands of years, and this plot of erosion rate versus time scale. And they also went out and measured sediment that was coming out of really small streams in this landscape and found that if you trap all the sediment over multiple years, it only makes up about 10% of that long-term erosion rate. And so they hypothesized that there must be some large episodic event that's required in order to keep pace with this long-term scale erosion rate. Then in 2016, Orman Pelletier went out and measured 2 burned watersheds in New Mexico that produced post-fire debris flows and found that that intermittent post-fire erosion was able to account for that missing 90%. And they calculated that if a fire were to initiate every 300 years and produce debris flows, it would account for 90% of that long-term rate and average out over the long period into these long-term erosion rates for the landscape. And Anderson et al. In 2015 showed that for an exceptional 2013 Colorado front storm, you were able to produce the equivalent of 150 to 2,200 years of background erosion rates. So if a storm were to occur once every 150 to 2,200 years, if that same storm were to occur at that frequency, you would produce your background erosion rate with no other erosion happening. So for these landscapes, rare storms and intermittent fires produce the most erosion and do the most damage. And I wanted to ask, is that the same process that we're seeing happening in the Dodson catchments, or does the proportion look different? And so I built a similar erosion rate compilation in the Dodson catchments over 1 to 1 million years. And to do this, I needed to calculate erosion rates over multiple timescales. And to calculate erosion rate, you need a volume eroded, the source area that that volume is coming from, and the time interval that you're averaging that out over. And there are a few key geologic events that I can use to constrain erosion rates over the long run. And so we know that the last major eruption in Dodson occurred about 1 million years ago, and the edifice that eruption came from is right at the apex of these catchments. And so I can use this relict paleosurface to construct a what that surface might look like at the time of the eruption, and take the modern surface and subtract it from that reconstructed surface to get a volume. And then I know all the catchments, I know the area of all the catchments that these volumes are coming from, and I can average out that amount over 1 million years. And then in the Columbia River system, we also know that Missoula floods were running out anywhere from 20 to 15,000 years ago. And just a mini Missoula flood refresher, at the end of the Pleistocene, the continental glaciers were extending down towards northern Washington. And as those were melting and retreating, you had glacial lake really large glacial lake outburst floods that were flowing through the scablands of eastern Washington, and all of those flows were siphoned through this location of the yellow star, which is where the dots and catchments are. So this really narrow area of the gorge is receiving all of that water that's coming through these glacial-like outburst floods. And if you model the peak water flows of where we are in the dots and catchments, Benito and O'Connor showed that it's about 200 meters above sea level for these catchments. And so if we conceptualize that on some Google Earth imagery, the modeled maximum Missoula flood stage is about at the apex of all these fans. And so we assume that maybe the Missoula flood scoured to bedrock near these dots and catchments, and these debris flow fans were not able to form during these flooding events. And so the onset of these fans occurred about 15,000 years ago. So we have a time constraint, and then we can get the volume of the fans through elevation profile mapping, and also getting the base of these fans through interpolated well data, and then get an erosion rate since the last 15,000 years. And then furthermore, we also have data from 1996 to 2001, which is primarily that 1996 and 2001 debris flow events that I had shown you earlier. And we know that this inventory is a little bit biased because we know that there are numerous non-infrastructure impacting reports and observations that were missing in between all these really large infrastructure impacting events that you can see from imagery. And then from 2009 to 2022, we have our differential LiDAR data where we can get very explicit volume data and miss no events using those data sets. And so these are our decadal scale erosion rates. And then if I plot my results in the same format as Orman, Pelletier, and Kirchner did, where I have erosion rate on the y-axis and measurement interval on the x-axis, my first result is from the edifice reconstruction rate, so E of that million-year time scale. And we see that it's consistent with that long-term uplift rate that I cited at the beginning of my talk of 0.2 millimeters per year. And then if we look at our first post-fire period from 2021 to 2022, excuse me, we see that that post-fire erosion rate is exceeding the long-term rate in most catchments by almost an order of magnitude or even more. And if we look at the entire post-fire period from 2018 to 2022, we see that erosion rate is sustained. So we're still about an order of magnitude higher for most of the catchments, with one outlier with few events. And then from 2009 to 2018, we see quite low erosion rates that are either on the order of our long-term uplift rate, or we also see no observations in 4 of our catchments. So quite a quiet period. And then with one outlier, also about an order of magnitude higher. So on average, about our uplift rate over that 2009 to 2018 period. However, if we add in the 1996 and 2001 events, so those Slido inventory events, we can see this increase in erosion rate in the events that do have observations over a 20-year measurement period. So we see the sustained high erosion rate regime in some of the catchments over a 20-year period. And what's most interesting to me is that over this 10,000-year time scale and our fan volume reconstruction rate, we see our 10,000-year rates are still exceeding our long-term uplift rate by over an order of magnitude, so by 5 to 50 times. And I argue that this rate is sustained by both post-fire and non-post-fire rates. And we can imagine this is maybe a transient signal that we're seeing in the landscape, perhaps induced by the Missoula floods. So if we imagined the Missoula floods coming in, wiping away whatever material was at the base of these catchments and initiating a nick point, we now have a new base level that is ripping through these catchments and all these debris flows are responding to. And our values are also comparable to other rapidly eroding landscapes. So if you think of the Illgraben in Switzerland that produces multiple debris flows annually and has really long-term background erosion rates, really high background erosion rates of 7 millimeters per year, we can plot that, and we know that debris flows are happening every year, so they're sustaining this long-term 10,000-year erosion rate, as we're also seeing in the dots and catchments. And then similarly to Orme and Pelletier, we can calculate our post-fire erosion contribution to this long term. We know we can pose that our duration of time that's experiencing post-fire rates is about 10 years, and then multiply that by our post-fire erosion rate, and then divide by our fire recurrence interval of 200 years. So fires are occurring about 5% of the time over the long term. And then we can compare that to our longer term 10 to the 4 year erosion rate. We find that the proportion of fire is less than 10% for most of our catchments. However, there is one outlier of about 40%. And if we look at a few of our catchments, that outlier is much more forested and was much more severely burned than Ainsworth and Tumalt. And this could be due to a more coherent forested system and a more soily system that might be actually able to feel the impacts of a fire more so than these cliffy bedrock systems. And so just some more tangible post-fire observations is maybe the sensitivity to burn severity in this Levens Creek catchment. So this is a map of Levens and Tumalt with burn severity plotted, and also those two differential LIDAR mapped debris flow periods. And you can see events initiating from severely burned areas in Levens, and also debris flows in Tumalt initiating from unburned regions. However, the events in Tumalt were much larger and they produced higher erosion rates. But Tumalt did not, it still had non-trivial erosion rates. They're still quite high. And then in Rock of Ages, we saw, in Rock of Ages, just a little bit west of Levens, we saw erosion rates that were a little bit lower, so about 0.3 millimeters per year, almost an order of magnitude lower than Levens and Tumalt. And Rock of Ages also had a ton of events pre-fire. So these green polygons are events that are occurring from 2009 to 2018, and it had very little post-fire activity. And so potentially it was a little bit sediment supply limited and is out of sync with Levens and Tumalt. And Tumalt had plenty of sediment, it was ready to go because it didn't have any events from 2009 to 2018. And so maybe also there's a negligible rainfall threshold change where Levens and Tumalt can produce debris flows for the same storm, but it doesn't need to be burned to produce debris flows. And so we're seeing decadal recurrence intervals for infrastructure impacting events out of these catchments, which means that there must be some process that's rapidly replenishing sediment in these systems. And from a lot of the work that I've done, I've seen a ton of bank failures in the field and also from helicopter imagery that's showing, after debris flows run down main stem channels, they're destabilizing a lot of these banks and inputting sediment and trees and large woody debris into these channels. However, that can also be a result of a loss of root strength, or you might be exacerbating this effect, which is maybe what we're seeing in Levens. And so that brings me to my conclusion slide, where Dodson catchments we find eroding 5 to 50 times faster than the original uplift rate over a really long period of time. And that's potentially induced by some base level modification, potentially by the Missoula floods. We see a contribution of post-fire conditions to these rates is about 5%, except for Levens where we see 40%. And that might be aided by the increase in debris flow magnitude due to loss of root strength along banks. However, sediment supply can still be limited in places like Rock of Ages, even under post-fire conditions. And thus sediment supply is really what's key to influencing the debris flow frequency here. And just a much broader takeaway, the gorge may have this really unique history, but our observations can still hopefully inform other post-fire responses in steep rocky landscapes that are burned in the Pacific Northwest, such as regions in British Columbia, where you can see these forested rocky slopes above really large debris flow fans and really big flows coming out of these systems. And with that, I will hand it over to David and we'll take questions at the end. Thank you.
Thank you so much, Maryn. Everything played absolutely smoothly, just so you know, while we're waiting for David to pull up his slides. Wow, that's got to be the fastest transition I've ever seen. So yeah, take it away, David. Oh, and David.
Okay, now you can hear me, right?
Yeah, you're good. You're good.
Okay.
You're unmuted now. Yep.
Okay, so hi everyone, my name is David Souza and I am a PhD student at Oregon State University. And today I'll be sharing some of my research from the past 3 years, focusing on post-fire root dynamics and landslide impact in Western Oregon. So Maryn has done a fantastic job explaining the landslide activity at Eagle Creek over long timescales, including how sediment from landslide contributes to channels and affects the breathable magnitude. And my focus will be on wildfire as a geomorphic agent at shorter timescales, specifically looking at its influence on landslide initiation by evaluating changes in root strength following wildfires. So with this extensive Eagle Creek LiDAR dataset, we analyzed how the loss of root strength affects landslide initiation, focusing on specifically unmapped shallow landslides features. So we have filtered the data related to shallow landslides for each epoch, pre-fire, 3 years post-fire, and 4 years post-fire. And by differentiating the before and after DEM and with the ground and slip surface, we could measure features like thickness, slope, and volume. And we have used this data to explore apparent root cohesion post-fire using back analysis. In this analysis, we used a fixed friction angle to simplify calculations, which was measured in the lab. And we tried to focus on finding the necessary cohesion to reach a factor of safety of 1 by using a 3D model with the simplified Jambu slope stability equations. We have specified cohesion values for a shallow depth of 1 meter, a range associated primarily with root cohesion. This approach allowed us to estimate root cohesion for each landslide and build a data set for each epoch. So these are some preliminary results from the second chapter of my dissertation, focusing on dry conditions. We are currently exploring other factors like rainfall thresholds, hydrology, and burn severity, which I hope to present in other opportunities. But we can get a lot of information from this result. So these show cumulative distribution of apparent root cohesion for each epoch. And it reveals that the root cohesion is similar for weaker 50% of the landslides, but it diverges at high values when comparing unburned with burned. So if we consider the 90% probability, root cohesion is slightly higher before a fire than after, with a modest recovery a few years later. And the maximum storm precipitation for each epoch doesn't suggest a strong forcing after fire. However, if we adjust for storm infiltration, this distribution will further diverge. So some takeaways observed from Eagle Creek suggest vegetation as a control on shallow landslide following wildfire. And this brings up an important question. How can we measure the decrease in root strength after a fire and link this decline to a timeline? And maybe use it to evaluate a landslide risk? The answer, a lot of hard work, digging test beds, getting muddy, and collecting roots for testing. So we took on this challenge to track how root strength changed after a fire, and we tried to understand the impact of wildfires on landslide hazards. So to best address the change in root strength, we choose sites burned in different years, allocated in hilly landscapes prone to landslide, all of them national forest areas, ideal for studying landslide risk. We have selected some major wildfires sites across the region: Eagle Creek in 2017, Holiday Farm in 2020, and Cedar Creek in 2022. Each of these megafires provide unique conditions, helping us evaluate different factors that influence landslide initiation. So this picture shows the tinsel device we have used to measure root strength and displacement, which helped us to create what is called a stress strain curve. So this allows us to understand how much the root can stretch and how strong they are at different sizes. So we have analyzed 970 roots from 26 testbeds, including both burn and unburned areas. The time since fire ranged from 4 months to 6 years, with roots diameter from less than 1 millimeters to 30 millimeters, and capacity from less than 1 kilograms to 450 kilograms. In coniferous forest, most of the roots are found on top half to 1 meter of soil, and this can be easily described in these root density graph at different depths for unburned areas and different stages post-fire. It is evident that burn sites show reduced root density, in particular near the surface, and root density decrease with depth. Another way to explore it is through median root diameter, which supports our finding on root density. As shown in this graph, median root diameter tends to increase over time after a fire. For example, in unburned areas, the median root size is 3.9 millimeters, but at Eagle Creek, it grows to 4.58 millimeters. So both root density and median diameter suggest that the smaller roots decay faster, while larger roots are more resilient. So to evaluate root strength, we considered the root diameter and the force required to break it. So in this graph, its strength, max force, is plotted on the y-axis with diameter on the x-axis. As expected, the necessary force to break larger roots grows exponentially. And also, our results align closely with data on healthy Douglas fir roots from Schmidt et al. 2001. 1 year after fire, we see that the relationship between root diameter and tensile strength remains quite similar when compared with unburned. 2 to 3 years after fire, it starts to see a significant drop. And 5 to 6 years, this drop is more accentuated. So when we plot the diameter strength relationship for different stages after fire, interesting patterns emerge. So for unburned roots and roots 1 year after fire, the strength diameter relationship are quite similar. However, beyond the first year, root strength declines rapidly. So this raised some questions. Are those burned trees still alive or just hanging on before eventually dying? So some potential reasons to explain this behavior include delay mortality, where trees take some time to decay, perhaps slowing down the root degradation at initial years. If we look at the overall tensile strength in this table, we can observe an initial drop followed by a plateau, which may be due to low root density, which brings up to another question. So is the relationship diameter strength representative to fully describe root capacity? The answer is probably not. When modeling root stabilization on slopes, we often assume that all roots break at once, but in reality, larger roots are stiffer, while smaller roots are more flexible, which brings up an important element to be considered, displacement. So by using models like fiber bundle model, we can explore root strength and at the same time account for displacement to fully comprehend the different capacity states of individual roots as they displace, and also as a group of roots in a system, and see how strong or fragile it is. But why is this important for landslides? So let's make an analogy. So imagine that you are swinging in a tree branch, and if the tree is alive and healthy, the branch will be more flexible and you have more give. But if it's dead and brittle, it will be more likely to break. And that's what you should consider about the importance of roots and landslides. So as a body of soil moves, the roots are responsible to hold that tension. And if the roots are alive and healthy, they will be able to secure this tension for larger displacements. But if it's brittle and weak, it will break at small displacements, triggering a landslide at minimal movement. So diving into the progressive breakage results, this plot shows load on the y-axis versus displacement. On the x-axis, this is average of off-root systems. The greenish blue curve, the highest one, represent unburned roots moving to Cedar Creek, the light green, Holiday Farm orange, and Eagle Creek dark red. We see that there's a steady drop in peak strength and a quicker decline in displacement, and showing that there are more bruteness over time. So another thing to consider is, like, you can use this as an useful trick, is that we often overestimate root strength by about 2 times if we don't account for progressive breakage. And this might be something that you want to consider when you're using root diameter relationship and you want to account for this progressive breakage. We also have plotted tensile load for dead roots. In this plot, we see Cedar Creek being recent burn has the strongest dead roots. And we also have data on recovered roots, allowing us to explore how root system regain its strength. So now we can look at this and start to think about things over time. So what is changing and how can we use this on some predictions? So we see the scattered data point representing the results from the video test beds on the overall root strength. And you see those big black circles, they are representing the max tensile load for each condition. I'm just gonna back one slide so you can see those big black points. It's the max one. And if you look at the fits, we can observe a noticeable decline across our roots. And for dead roots, this trend becomes even more distinct. And to analyze this further, we can apply some classical methods. We can infer recovery roots by the difference between overall roots behavior and dead roots behavior. This approach allows us to model separate functions for recovery roots and dying roots, which when combined can represent the overall root dynamic more comprehensively. So by taking these functions and extrapolating by a time of 50 years, we have multiple perspectives to consider. So in this figure, we see 2 superposed curves representing overall root strength. And we see that a weaker point where we lose about half of our root strength. So for medium root conditions, we generally see root strength reaching its lowest point within 3 to 5 years time frame. This is a zoom from this part. And for recovery, while variable, follows a general trend, about 12 years for 50% of recovery of strength and 25 years to reach 90% of recovery. Of course, there are some error bars applying to those estimates, but this provides an useful framework for understanding root dynamics and recovery patterns over time. So when we parameterize a slope stability model, we typically use strength parameters like cohesion and friction, and we often use root cohesion as a key factor. And that's what we're going to be using in our slope stability analysis. Okay, so we can apply this to a basic slope stability model called the infinite slope model. This equation is an alternative for infinite slope, accounting for lateral root cohesion. So think of it as a simple slab that accounts for thickness and heel slope angle to determine if the slab is stable or not by calculating a factor of safety, which essentially tells us the stability level. So if it is above 1, the slope is stable. If it's below, it fails. So now looking at this plot, the y-axis represents the slope of the slab. I call attention to the x being inverted. It caused some confusion in previous presentation, and I know, pig-headed or too lazy to change it. And okay, so anyway, the x-axis shows the saturation rate, which is the portion of the slope saturated with water. And we calculated the factor of safety for all combinations of saturation ratio and slope, considering root cohesion. So in this graph, we see an example of pre-fire condition, when the green area represents combination results in a factor of safety less than 1. We also apply the same process for post-fire conditions, keeping the same combination of saturation ratio and slope, but this time considering the minimal root cohesion. And the unstable condition grows from this green area to this red one. So now think of this way. So if we subtract the green area from the red area, we get a band that represents a condition that became unstable due to the loss of root cohesion. And this highlights the critical impact of root cohesion loss on the slope stability. So each of these bands represent pairs of slope and saturation ratio that prior to the fire offered a stable condition to the slope, but after the fire, it became unstable. And we did it for different friction angles. To explain this conceptually, as root cohesion weakens, the slope that were previous stable may begin to fail. Okay, so another important way to look at the impact of root cohesion loss on landslide initiation is by examining scenarios where this loss really affects slope stability. So let's take an example with this point 1. This is a point that was stable prior to the fire, so this is fire initiation. But after fire, even with the same conditions, it becomes unstable at a lower level of saturation ratio. And this tells us that within 2 to 4 years, where is our danger zone is, the slope could fail with less moisture in the ground. Essentially, this means that at a smaller storm, something that might not have been a problem before could now trigger a landslide. We also see changes in slope behavior post-fire. Once again, this slope axis is inverted. For instance, slopes that were stable pre-fire may now fail at gentle slopes, showing that more areas might be at risk for landslide after a fire event. Okay, so these insights highlight how significant the loss of root cohesions can be, making previous stable areas more susceptible to landslide due to even minor environmental triggers. So, okay, so some conclusions that I have is that root strength decrease after wildfire due to combination of root decay and regrowth of vegetation. Unburned root systems tend to be more ductile compared to those affected by fire. Root strength and ductility appears to reach the minimum around 3 to 5 years following wildfire. Also, larger uncertainties for recovery related to revegetation. And vegetation, it's only one element in the role of fire as a geomorphic agent in Oregon. So plenty of change in these steep soil metal landscapes. Okay, so I want to say many thanks to everyone working on this project. And if you have any questions for me and Maryn, we're going to be here.